Hello, everyone, and welcome to today's exciting session. I'm thrilled that you're here, taking time out of your busy schedule to deepen your knowledge of machine learning. Today, we are going to explore a technique that combines intuition, simplicity, and power in a beautiful way, the key nearest neighbors. Whether you are just beginning your machine learning journey or looking to refresh your basics, this session is designed to give you clarity and build your foundation and spark new ideas for your future projects. By the end of this video, you'll not only understand how KNN works, but also why it's often one of the best first choices when tackling real-world classification and regression problems. Let's dive right in. K nearest neighbors, often abbreviated as KNN, is one of the simplest and most straightforward supervised machine learning algorithms. What makes KNN truly unique is that it's a lazy learner, which means it doesn't actually learn a discriminative function from the training data, but memorizes the entire dataset. When a new observation needs to be classified or predicted, KNN searches through the source code in training instances to find the key data points closest to the new point and makes a prediction based on their characteristics. It's a non-parametric algorithm, which means it makes no underlying assumptions about the distribution of data, making it extremely flexible and useful across a wide range of applications. KNN works for both classification, where we predict a discrete label, and regression, where we predict continuous outcomes. At its core, KNN is built around one of simple ideas. You are most similar to the closest to you. In classification tasks, KNN is often compared to having a group of friends to help you make a decision. When a new data points needs to be classified, KNN identifies the k closest points in the training data and checks which class is most common among them. The new data point is then assigned to the majority class among its k nearest neighbors. The voting mechanism makes KNN extremely intuitive. There are no complicated equations handling in the background, just a straightforward process of comparison and majority decision making. However, the choice of k is very important. Too small and the model becomes sensitive to noises. Too large and it may include points from other classes. Finding the optimal k is key to building an effective KNN model. Let's go a little deeper into how the KNN classification process works. First, you select a k value, typically a small odd number like 3, 5 or 7 to reduce the chances of a tie. Next, when a new observation comes in, you calculate the distance between this point and all other points in your training set. Then, you sort all the distances and pick the k smallest ones. Finally, you look at the small classes of these k nearest points and assign the most common class as the prediction. It's like moving into a new neighborhood and asking the majority of your neighbors what the community rules are and assuming that that's what you should follow. The most common way to measure the closeness between the points is the Euclidean distance. Imagine a straight line connecting two points. That's Euclidean distance. In a two-dimensional space, the formula is simply the square root of the sum of the square differences between the corresponding features of 2 points. It's the most natural and intuitive way for us to think about distance, just like measuring with a ruler. However, as dimension increases, the interpretation can get tricky. But for most low-dimensional data, Euclidean distance serves as beautiful. Another important way of measuring distance is Manhattan distance, also called as L1 distance or taxi cab distance. Instead of thinking in terms of straight line, imagine navigating through a city grid, moving only along horizontal and vertical streets. Manhattan distance is simply the sum of the absolute difference between feature values. This method can often outperform Euclidean distance, especially when the data set has many dimensions, or when the data points have features with varying scales and outliers. Choosing between Euclidean or Manhattan distance often depends on the problem at hand and should ideally be validated as using cross-validation techniques. KNN is not just limited to classification. It also performs regression tasks effectively. In regression, instead of voting for the most common flavor, KNN averages the output values of its k nearest neighbors to make a prediction. This allows KNN to predict continuous quantities like housing prices, stock values, or any other numerical outcome. Again, no heavy mathematics involved, just simple neighbor-based thinking. KNN regression is especially helpful when the relationship between the features and targets is too complicated for a simple linear model, but doesn't require the complexity of more advanced methods like neural networks. The process of KNN regression follows a similar structure to classification with a slight difference in the final step. Once the k nearest neighbors are identified, instead of checking for the most common label, we compute the average, or sometimes weighted average, of their output values. This average value becomes the prediction for the new data point. It's like asking your closest neighbors for an estimate of their home values and averaging them to predict the value of your own property. Simple, logical, and often surprisingly accurate for a broad range of real-world regression tasks. While Kn's simplicity is a strength, it comes with a cost. It can become computationally expensive as the size of the training data grows. Since KNN searches through the entire dataset at prediction time, it can get slow for large datasets. Thankfully, researchers have come up with efficient variants to speed up the neighbor search, namely KD trees and ball trees. These data structures allows us to organize data in a way that dramatically reduces the time needed to find the nearest neighbors, making KNN practical even for large datasets. A KT tree, short form of k-dimensional tree, is a binary tree that recursively partitions the features into feature space into tested half spaces. At each node, the data is split based on the median value of the particular feature, alternating feature at each level of the tree. When searching for neighbors, we can quickly eliminate large points of the tree that cannot possibly contain the nearest neighbors, allowing for faster queries. KD tree works exceptionally well when the number of features is relatively low, typically under 20 or so. For low-dimensional data, KD trees are a fantastic way to make KNN lightning fast. Now, instead of splitting the feature space along dimensions, all tree groups nearby points into hyperspherical clusters called as balls. Now, each node of the tree represents a ball that encloses a subset of points. When searching for neighbors, we can quickly eliminate entire balls that are too far away. Ball trees are often preferred over KD trees when the number of dimensions is high, as they handle the cost of dimensionality better. In both cases, these clever structures make KNN a lot more scalable and efficient. KNN is one of the most versatile machine learning algorithms and has been applied successfully across a variety of domains. In healthcare, KNN is used as used to diagnose disease based on patient symptoms and medical data results. In finance, it helps in credit scoring, fraud detection, and identifying loan risks. In recommendation systems, KNN helps us suggest movies, products, or music based on user preference and behavior. In image recognition, especially in early days, KNN was heavily used to recognize handwritten digits like the MNIST dataset. The takeaway here is, whenever you have a labeled dataset and a new observation to classify or predict, KNN is often a reliable starting point. Now let us recap what we have explored. K-nearest neighbors is an extremely intuitive, flexible, and non-parametric supervised learning algorithm. It works by finding the k most similar data points to a new observation based on a distance metric and either voting or averaging to make a prediction. Euclidean distance and Manhattan distance are the most commonly used similarity measures. For large datasets, smart data structures like KD trees and ball trees make KNN scalable and efficient. KNN has found success across industries, providing that sometimes the simplest algorithms are the most powerful. KNN is a timeless classic, that is, one that teaches us the elegance of simplicity in machine learning. Thank you so much for joining me today and walking through the world of k-nearest neighbors. I genuinely hope this session has added value to your understanding and made the concepts behind the KNN feel simple and approachable. If you found this presentation helpful and would like to learn even more about machine learning and AI, I invite you to connect with me on LinkedIn, where I regularly share insights, tutorials, and career tips. And if you want to dive deeper into hands-on projects and real-world applications, subscribe to my YouTube channel for frequent tutorials designed to help you grow in your data science journey. Let's continue learning, growing, and building amazing things together. Thank you once again, and I'll see you in the next session.